This is section 4.5. We're going to be talking about routing algorithms, looking at link state algorithms, distance vector algorithms, and then talk a little bit about hierarchical routing. For today, we're going to start with a little introduction and then talk about link state. So we talked about the two key functions at the network layer, which are routing and forwarding. Remember, forwarding is a very local process where we say, given this input port, what output port should I forward this to? Local. Whereas a routing algorithm is the piece, it's the software that is solving the problem of global paths. How do I get from one endpoint to another endpoint over multiple intermediate paths? You see there's a clear connection between these two, though, because whatever your routing algorithm is going to create the forwarding table so that global knowledge gets distilled down to, so you have local knowledge as well. All right, so the whole end-to-end path matters for local decisions. And we can see how this routing algorithm is creating this forwarding table that says, okay, if the header value of the IP address starts with these values, then you go to this particular output link. And forwarding can be done very quickly, whereas routing is going to be more complicated. In order to help us with routing, we're going to use math. I know that's scary, but it really does pay off this time. And we're specifically using graph theory, where graph theory says we're going to represent a graph as a set of nodes and edges. So this is like graph theory 101, super basics, and you may have studied this in other math classes. What we're looking at here is we have a graph is nodes and edges. In our case, routers are going to be represented by nodes. In this diagram, we're representing them with routers A through E. That make sense? Edges are links between the routers. So we can identify those with the two routers that connect. So we have edge AB, which is this guy right here. We've got AC, which is here, and so on and so forth for all the others. So you see how we're mapping a network topology into a graph. Does that part make sense? The additional thing we've added on here is we have set a cost for each link. Those are the numbers that are written next to the links. And these costs represent, in some way, how long it takes, somehow the goodness of that link. We'll talk about in a second how that might be related to the real world. For our case, we're going to use this abstraction as a way to solve the problem, how do I get from source to destination over multiple hops in between in the best way? So our question is, what is the best path, say, from A to E? So we're going to assume that A is our source, E is our destination. How do we get from A to E in the best way? Now, what do we mean by best? Well, that's important to define. In this case, we mean the least cost path. What's the least cost path from A to E? You're intelligent people. Look at this diagram and tell me what is the best path, the least cost path from A to E. You can see there are several different options, so you kind of do trial and error and figure out what the best one is. What do you guys see? What's the best?
A to B, B to C, C to D, and D to E.
All right, what's your total cost? Your total route cost?
9.
2 plus 1 plus 4 plus 2, which is 6, 7, 8, 9. Link, oh, sorry, this is messed up. This is 10. It should be 1, 0. I'm sorry. Sorry about that. My formatting got you there. Right, so if it were 1, it would be A to D, D to E, because that would be 3. That would be our best. Since it's 10, sorry about that. My bad. It's actually 12. 12 is more than 9, so we don't like that as well. Notice we can also do it in 11, A, B, E, as well as many other possibilities. But Brennan was right. The best one, I believe, is in 9, which is A, B, C, D, E. There's something nice about that ordering, isn't there? I didn't mean to do that. Notice there are more hops in that case. We're going through more routers than this ADE, but because we're saying we want the least cost path, which is based on these weights. The A, B, C, D, E path is the best. Okay, so we're going to talk about two types of algorithms that solve this problem. The first is link state, and the second is distance vector. But I wanted to kind of give you an overall picture of a comparison between those two classes of routing protocols, routing algorithms. I use routing protocols and routing algorithms interchangeably. I don't think that's inappropriate, but if it's not, then it should probably be algorithms. Okay, so the first class we're looking at is link state. In order for link state algorithms to work, the node has to know the complete network topology. That means it has to have that complete picture of the network, like we saw in the previous slide. You've got, all the links, all the connections, and all the costs between them. How do you get that information? Well, in order to have that global knowledge, you can see that keyword global here as well, you've got to broadcast the link information to everybody so everybody has it. And then everybody can independently, right, within themselves, each router can run the same algorithm using the same input information, which is all the link costs, and end up with the same results. I like to summarize link state algorithms with this little phrase. Link state algorithms tell the world about their neighbors. All right, so they have to broadcast the information about their link states to everybody so that everybody has it. In contrast, distance vector routing protocols are very local based. So they can get by with knowing just the local topology. That is, I know about the links to my one-hop neighbors, and that's all I have to know. Instead of broadcasting information, distance vector algorithms exchange information among their neighbors. So that would be a lot less communication. Instead of sending it to everybody in the whole network, I just have to exchange information with my one-hop neighbors. Thirdly, distance vector is a very decentralized algorithm, so everybody's doing it. There's no central authority, there's no central database. That's kind of being developed as the information propagates, but it's not, link state is not decentralized because everybody has to have the complete topology. The way I like to sum up distance vector informally is we're telling the neighbors about the world. So each person has, that is, each node has a distance vector, which is a list of costs to every node in the network, but it just has to send that distance vector to its one-hop neighbors. Just have to exchange that. So we're telling just our neighbors about the whole world. And over time, that picture of the whole world becomes more and more correct and clear. And that's the way distance vector works. Another way to classify algorithms, as pointed out in the book, is if they're static or dynamic. Static algorithms are adapt very slowly to changes in link costs, whereas dynamic can quickly update to link changes. So that could be if a link goes down and all of a sudden you can't route packets over that link because it's disconnected, so it has like an infinite cost, right? We don't want to go over that link. How fast would that update? Also, if things just periodically change, does the routing algorithm adapt? A little more notation, introduction. We're talking about the least cost path. This is the book's diagram. It always is going to be computing between U and Z. This is a little bit more complex a network than my example. The book uses this notation, C of WZ, which means this is the cost between W and Z. So you can see CWZ is 5. Yeah? How do we compute that cost, these numbers that are all over the graph? These could be computed in several different ways. 3 that the book points out is, 1, they could be constant, which means just give every link a 1. In that case, the least cost path is actually the what? The shortest path. So if that's what we care about, we can easily do that by we can use the same algorithms to compute the shortest cost path, not shortest cost, the shortest path by just setting all of the weights equal to 1. Yeah? We might also set these costs based on bandwidth. So we would give a higher cost to the links that have smaller bandwidth, the slower links. So that way we would prefer larger, faster links. Does that make sense? And lastly, it could be congestion related in the same way. If we have some way of measuring congestion on a link or at a router, we could say, hey, if you have high congestion, then you have high cost. And our routes will then adapt to that congestion. Okay, any questions about this intro stuff with routing? All right, so let's look at the link state algorithm. First, let's summarize in words and in pseudocode, and then we'll look at a visual example. All right, so we're going to look at one particular kind of link state algorithm, Dijkstra's algorithm. He's a really famous computer scientist from back in the 60s. He's a super smart guy and came up with this very elegant algorithm to solve this graph problem. Dijkstra's algorithm requires global knowledge. That is, you have to know all of the costs of all the links. Yeah, got to have the complete network picture in mind. When you have that, we can run this algorithm, which runs in an iterative fashion. That is, it's going to be a for loop, basically, that goes through and gets better and better and better solutions. But all that iteration is happening locally with the same input information, which is the set of link costs. Our goal is to find the least cost path. Say what Dijkstra's algorithm is going to find is the least cost path from some source node. You can imagine this being, this is the node that is running this algorithm, to every other link, every other node. So I'm going to find the least cost path from me to everybody else. Make sense? As I said before, in order to have this global knowledge, you're going to have to do some kind of link state broadcast so that all the nodes have the same information. But when we're done with this, it's very easy to create a forwarding table to say, okay, if I'm going to send nodes, if packets are addressed to this particular address, I know where to send them. I know which output port to forward them to. All right, that's what we're going for. Okay, I know this is sort of a beast to look at. I mean, it's really, like, 16 lines of code is not that much, but it is jam-packed with algorithmic complexity. The idea here is that we're going to create a set called n prime, which is the set of nodes for which we know the route to. All right, these are the set of kind of known nodes. So initially, the only node that we know a route to is the source. Okay, S is the source. That's kind of me, the guy who's running this. We're then going to go through and find all of the nodes adjacent to S. That would be all the one-hop neighbors of S. And for each of those, we're going to set the distance to that node equal to the cost from the source to that node, which just means for our one-hop neighbors, we're saying we can get to you in a global way. That's what you could kind of imagine. The D cost is the distance, which is the global least cost. And if it's a one-hop node, we know we can get there in at least, right, in the worst case, by going directly to that link. It might be better to go through somebody else, but we don't know that yet. But initially, we're going to initialize them to D of n equal to the cost from S to n. If you're not a one-hop neighbor of the source, then we're going to set the D of n, the distance to n, equal to infinity. So that means, right, we've got this huge distance. Whenever we find a smaller distance, which is what that loop is going to do, is iterate through searching, we're going to update that. Anything that's smaller than infinity, which would be anything, right? But we'll just keep doing that. So this is the initialization. This is kind of what we set up before we run our algorithm. Questions on that? Okay, let's get into the loop. Step one, we want to find and select some node M that is not an n prime. Initially, this would be all the nodes. Yeah, because only S is in Well, all the nodes except the source. So initially, n prime has just the source, so we're going to choose some m such that d of m is the smallest. So we're looking for the node in the set, n prime, that has the smallest d value. So who's that going to be? That's going to be whichever of our one-hop neighbors has the smallest cost initially. Okay, at this point we're going to add node m to our set n prime. We can imagine in code we would be doing this with arrays or something. Right? But this pseudocode, you can think about it however you want, that this is just a set and we're moving things to different sets. And we're keeping up with a little bit of information, right? Like we could imagine this dn maybe another array, or it could be an object or a structure that keeps properties of each node. All right, now we're going to update dn, that's the cost to n, for all of the n adjacent nodes to m that are not in n prime. All right, so we're going to look at all of the one-hop neighbors of m, which we've chosen up here, node m. We're going to look at all of its neighbors, look at all the one-hop neighbors of m, and update their dn value based on this formula. This looks a little complex, but it's super simple if you think about it. It's just what your intuition would lead you to believe. We're going to say the new dn value is whichever is smaller, the current dn value or the cost to get to m plus the cost to get from n to m. So we know we can get to n in dn, that's its previous value, but if one of its neighbors, if the cost to get to one of its neighbors, dm, this is from the source to dm, plus the cost to get from n to m, if that's smaller than the cost to go directly to dn, then this is the better path. Yeah? So we're going to remember which one, what's our smallest cost, and remember which node we went through to get to that. This is just a comment you see. The new cost to m is either the old cost or to m or the known shortest path cost to n plus the cost from m to n. We're going to store, this is what I was saying, we're going to store the previous node, that's p of m is the node that's previous before m that we go through to get to this path. So at this point we will have found a better path to n. At the end of this loop, we will, we're going to come back and do this again. Now, though, we have one fewer node we have one more node in n prime, whatever the one that we found before. So now we have a smaller set, and we're going to keep repeating this until all of the nodes are in n prime. So this is a really elegant algorithm. Do you have questions on this right now, or are you ready to see the visual version first? Visual, all right, visual for the win. Okay, hopefully this will work. This is our network again. This is our topology. I'm sorry about this. Sorry, this is 10. Once again, we're going to say A is our source. E is kind of going to be our destination. But it doesn't really matter because what link state is computing is the shortest cost path from some source node A to everybody else. Right? That's what we'll come out with. So what I'm going to do is I'm going to put our graph up here for reference. Again, this is 10. And then I'm going to put some new notation on this. I'm going to denote nodes in n prime, the set that we found in the red color, brown color, whatever you call that, and then these are not in n prime. Also, for each node, I'm going to remember two things. I'm going to remember the cost to it and the previous node to get to it. All right, so let me show you where we start. Okay, so if we look at this, we see that we can get to B with 2 through A. So this 2 is the D of M, but it's really the D of A, the distance, and not A, it's the D of B. And A is the P of B. All right, so really, that notation gets a little bit ugly. Maybe it's certainly to say. The two things we're keeping up with are what's the best distance that I've come up with so far, the least distance, and what's the previous node associated with getting that distance. So initially, right, the two one-hop nodes of A, sorry, there's three one-hop neighbors of A, have these three values, right? We can get to B in 2, we can get to C through A in 4, we can get to D through A in 10. Does that make sense how I got those three values? All right, so now what do? We choose the minimum D, which is going to be, oh, sorry, so the last thing is, right, we can't get to E at all. It's not a one-hop neighbor, so initially it has a cost of infinity, and there's no previous node associated with that. Okay, so we're going to choose B as our new node, kind of our active node. That's what light blue means. We choose B because it's the least. It has the smallest D value, 2, right? 2 is smaller than 4 and 10. At this point, we're going to update and check, okay, well, how, if I get to C through B, how much is it going to cost? Well, it's going to cost the 2 plus the cost to get to B, which is 1. It's currently 4. I know I can get 4 straight to C. So what's smaller, 4 or 2 plus 1? 2 plus 1. Nice. All right, so that means we update and say, hey, this means I've updated this information, this color. I can get to C through B at a cost of 3. Make sense? All right, so let's keep going. Well, now we have to look at all of the neighbors of B. Yes? So next, right, I can get to D in 10 through A. Or I can go 2 here, 6 here, that's 8. So I can get to D in 8 through B. 8 is less than 10, so that's better. It replaces it. And lastly, I can get to E through B in 9 plus 2, which is 11. That make sense? Now these aren't optimal yet, but they're better. Right? So now let's go through the next iteration. So now we say, okay, this is a little bit different than the pseudocode, but I like this notation. Now I'm going to completely move B into n prime, kind of that I'm done with it. So now I need to select some other node, not an n prime, purple in our case, that has the smallest D. Looks like C is our guy. Yeah? So let's choose C to be our next active node. So now we do the same thing. We compute for all of the neighbors of C, not in n prime, which is only, what? Only D, does it have a better path? So I can get to D in 8 through B. How do I get to D through C? Well, that's going to be, this is 4 right here. Yeah? So that means I can get to D in 7 through C, because that's 3 plus 4 is 7. So I'm going to store here now that I can get to D in 7 through C. Yeah? Okay? Add C. C doesn't have any other neighbor nodes. Add C to our set and move on. Now, D is the smallest, so we choose D. We move to it, make it active. Check all of the neighbors of D that aren't in n prime. There's only one, right? And this says I can get to E through D at a cost of 7 plus 2. 7 plus 2 is 9. That's better than 11. So let's update that. Then E can get through. We can get to E through D with 9. Add D to our set. We still have one more node. We want to do it. So we make it active. It doesn't have any neighbors. So, we're done. Sweet. And at this point, we have analyzed the complete network topology, found the least cost paths from a source node A to everybody else. You can imagine here we could analyze the structure that's storing this graph and create a forwarding table for this to say, okay, if we get a packet at A that's destined to go to D, who should we send it to? Well, I mean, we can say, all right, D goes through C goes to B, all right, B goes to A, so I want to go B, C, D to get to B. So that means on this case, if I want to get to D, I need to send to B. That's what the forwarding table, all the forwarding table would need to know. We could take this a step further and kind of imagine that what we've stored is these are the best links in here that we really need to remember in dark arrows. And in fact, we could even take it a step further and imagine, let's just delete all those other links because we're never going to use them. We're always going to use this best path, this least cost path. So this is a subset of our graph that's really the best path to route to everybody. So this is link state algorithm using Dijkstra's algorithm to compute the least cost paths. And I hope that this gives you a visual idea as well as a coding idea of how this works. It's simple-ish and elegant for what it does to solve a hard problem. What's the best paths in this whole big graph? And this would work on any size graph. Right? We have really small graphs here. And when you think of link state, I want you to think about telling the world about your neighbors. Right? That's what this requires. That's the first step, which we already had, which is all of the link costs. And then we can run this algorithm and find the best paths.